I'm Quinn Spadola. I'm the Deputy Director in the National Nanotechnology Coordination Office, and this forum is actually co-hosted by the NNCO, by Mariel Kolker, who is an educator, a high school teacher from New Jersey, and by Daniela Duran at the Nano at Stanford site, and she's also a former high school teacher. The purpose of this forum is to share the resources that can help all of you introduce nanotechnology and other emerging technologies to your classroom. We do this through a couple of different ways. There are teacher-led discussions about resources, curriculum, and demos. There are also short informational talks given by teachers as well as experts in the nanotechnology field. And we also can talk about different cutting-edge nanoscience topics. For example, nanotechnology and climate change was a popular one a little while ago, and we're arranging some future ones. There's also opportunity to ask questions and to talk to each other as well. And I wanted to share that the NNCO and the National Nanotechnology Coordinated Infrastructure are going to be sharing a booth at the National Science Teachers Association meeting this March in Colorado. So if you're going to be at the NSTA meeting, please stop by and visit us. We're going to be in booth 772. Tonight, we're going to hear from Tom Pinnell from the Cornell Nanoscale facility. In addition to being a research support specialist in the clean room there, I know that Tom is also a very passionate advocate for education outreach and does a lot to inspire students. And he's going to tell us about a virtual clean room tour and demos that you are free to use to teach your students about nanotechnology. But before we get to Tom, we have a special guest tonight. We have Dr. Jay Vitas. And Jay is the chief of the Emerging Technologies team in the Division of Sciences Integration at the National Institute for Occupational Safety and Health. And he's joining us this evening because NIOSH recently released some guidance on the safe use of 3D printers for schools and libraries. So we wanted to share this information with you so you can learn more as well as share it with your colleagues. So you're all using your 3D printers safely among your yourselves and your students. So I'm going to turn it over to Jay now. Thank you, Jay.
Great. Thanks, Quinn. Really appreciate the opportunity to talk with all of you here today, as well as to share a bunch of information about 3D printing. I put it all in a bunch of slides, and let's see, I'm going to get this going so that way hopefully you see the front screen there, and I'm going to run through it quickly, but these slides will be available for you to refer to and to share with others, and there'll be a connection to this document at the end, so that way if you have any questions you can refer to the document or you can connect with me. So just quickly, NIOSH is one of two occupational safety and health agencies that are at the federal level that you might be interested in knowing a little about. We are the research agency, which is different from OSHA, which is the regulatory agency. And we have a number of services to the American workers, and anybody that is occupationally employed is a worker, and so I welcome them to use any of these services as they desire. And we are located in a variety of locations, and I'm coming to you today from Cincinnati, Ohio, where we have probably the largest number of people that are employed. So we're going to talk about 3D printing and why does it matter? 3D printing is quick, an opportunity to turn computer models into physical products quickly. And what is wonderful about this technology is that it's now becoming available at really decreasing cost to individuals. And as a result, from an education standpoint, is becoming more common in the school and in classrooms. The most common forms that we're seeing as consumer products, or in the schools as well, are the fused filament fabrication process, in which there's some sort of plastic that is melted and deposited via a moving extruder onto a platform. And the platform essentially it moves downward, or I guess the product is built upwards, so then that product is built. The other way is through vat polymerization, in which some sort of photopolymer resin is in a tank, and then it's cured with UV projector or laser, and the platform is lowered into the resin, allowing for the building of these particular 3D models. So what are the potential hazards? I don't mean to scare individuals, but I think it's important for people who are working with these pieces of equipment that there are potential hazards associated with these 3D printers. And it depends on how you use them, where you use them, the number of 3D printers that are occupying a particular space, and then, of course, how well somebody understands the use of them in generals. The concerns that we have seen at NIOSH include potential exposures to volatile organic compounds and particulate matter. In some of the post-processing, there are solvents that are used that potentially could be harmful if used a fair amount. There's obviously heat that is used in these processes, so they can burn individuals if they don't understand where the heat sources are. There's a number of mechanical potential, moving parts that could injure fingers or could pull on loose clothing or hair. There's, I just mentioned in the photopolymerization process that there's lasers, and then associated with the lasers, there's electrical issues and noise. If, again, a number of these are all used in a small confined space or a space where the surfaces are very reflective, can cause a fair amount of noise hazards for individuals as well. And on occasion, these 3D printers are associated with some sort of robotic tool that helps to feed the materials into the device, and that may have issues with it as well. And then we see potentially, if you are working with these materials, that the volatile organic compound or the particulate matter could be brought home if there's a certain, if those get on your clothing, and then you bring them home with you as well. Now, our approach from an occupational safety and health perspective to reduce the likelihood of these hazards causing some sort of health outcome is through the use of the hierarchy of controls. And we always want to start at the top if we can, and work our way down to maximize guess you could say, the effectiveness of these controls. And the first one begins with that elimination and substitution. It's common sense, but not necessarily always understood, that you can use sometimes different feedstock that might have less amount of emissions from them, or less hazardous emissions. And so that's one way to deal with that. From an engineering control standpoint, and this is probably the one that most likely would be employed, is to have some sort of ventilation that is going to reduce the amount of, or increase the amount of air that goes through a space, but then reduce the amount of exposure to individuals. And you can create, if you have a number of these 3D printers, some sort of a contraption like is shown here on the slide, where you can control the airflow specifically and almost make exposures to individuals negligible to none. And we've actually, in this publication, described how you can take a 3D printer and actually print a part that can be attached to some other commonly available parts to create your own local exhaust ventilation system, so that you can actually reduce exposures to people who are working with these devices. And it's relatively inexpensive. I think that when we did this work, it was about 4 or 5 years ago, and cost about $60 for each device. So not too bad. And then there's engineering controls like lower printing temperatures, use of sticky mats, and some sort of to control particulates going in and out of an area, and then machine guards and interlocks. Administrative controls like training, not having people tie their hair up, or eliminating the use of loose clothing can be helpful as well. It's recommended to not have food or drink in these areas if possible, and then to obviously work with smaller amounts of quantity of materials if that is possible as well. And then to clean with wet wipes and high efficiency particulate air filter vacuums. That's ideal. Obviously, you can use other vacuums as well, depending upon the particulate size. And then to be prepared for what could happen in some sort of an unexpected situation where these materials could get like a vat polymerization, where it might spill into an area. Personal protective equipment could also be used, such as gloves, eyewear, and if necessary, respiratory protection we really recommend consulting with an occupational safety and health professional if you're going to go to the respiratory protection or laser eye protection as directed by the manufacturer. And most importantly, where can I find more? There's lots of information about additive material and 3D printing at our website. Also, a lot of additional information about exposures to nanomaterials and advanced materials that you can also find there as well. I've included the URL for the document itself, a QR code, and just our website if you wish to go there for further information. And then I welcome any email directly to me and my team at nano@cdc.gov. And with that, I thank you, and I welcome any questions.
Thank you so much, Jay. I think in the interest of time, because I know Tom has an action-packed presentation for all of us, I'm going to encourage everyone. We'll be sharing those slides. They can get to the QR code and check out the resources, and we'll make sure to share your email address. If people have any really pressing questions right now, please put them in the chat, and we can also forward them on to Jay for you. But I want to jump on to what Tom is going to be sharing next, because I know he's got a whole good hour of things. But thank you so much, Jay. And we'll be passing out more information at the NSTA about this as well. But please don't hesitate to reach out if you need anything else, because I think it's really important that we are using these tools safely.
Thank you.
Okay, Tom, take it away.
All right. Thanks, Jay. That was a great presentation. That's actually really important to have them in some sort of ventilated cabinet is pretty useful. And thanks to everybody for the invitation. I'm going to try and set the world record for most times sharing and unsharing my screen and jumping around. I've got a whole bench over here with a bunch of demos set up where I'll walk through them individually. I'll show a whole bunch of content that we typically show to students. And I'm going to share the slide deck at the end. So take what you like, use it, email me. I'll help you craft something for your classroom. More than willing to do that. So without further ado, share screen. We'll do that one. And let's see. Okay, the Zoom just turned off there for a moment. Okay, now I'm going to share my screen again. And I'm going to share audio.
We can see your slides, Tom, but we're seeing the display mode instead of presentation, or we're not seeing it as full. Yep, there you go.
All right. So welcome to the Cornell Nanoscale facility, my home away from home. I'm on the CNF technical staff, as was mentioned earlier, and I'm also the education and outreach coordinator. So a little bit about me. I'm on the technical staff where we train users how to safely use all this complex equipment that we have in the lab. And we assist them in making groundbreaking research. So we need to understand their goals and develop new and innovative processes that help them expand the scope of scientific understanding. And we diagnose and repair equipment when it inevitably gets broken. As the education and outreach coordinator, we're organizing and hosting events for all age groups. Last year, our facility hosted over, I think, 4,000 visitors, with a major portion of them being in the K through 12 age group. And so part of that is enabling educators to bring nano into their classroom and developing content that's appropriate for as many audiences as we can. So CNF, we're an open user research facility located on Cornell's campus, right in Ithaca, New York. We've been doing this for over 45 years, and our mission is sort of to enable rapid advancements in technology by providing all the tools and the expert staff needed to make these things happen. We generally have around 500 users a year. And we've got on staff over 500 years of combined technical experience in micro and nano fabrication. We're part of this national network, the NNCI, and we're funded by the National Science Foundation. So Here's some of our tools in the lab. I'm not going to focus on these, but one of the most important processes we do is lithography, where we're printing our designs. And then the other two main processes are deposition and etching. We'll sort of get into that in a minute. So we have all these lithography tools at our facility, and then we've got etching and deposition. And then for everything that we can deposit or etch away, we need some way to measure it, right? So we have all this interesting measurement technology in the lab as well. A typical youth outreach visit to CNF starts, it can be in person or virtual. So I'm happy to set something up with your classroom. We start by engaging the students, generally with something pretty simple. What's the smallest thing you've ever made? There's typically a 15 or 20-minute sort of intro to nanotechnology slide deck. Lots of pictures, animations, short videos that are meant to keep things active. And then we can actually do either an in-person or live virtual cleanroom tour. That tour can take a number of forms. It can just be a walking and talking tour, all the way to I've done hands-on device fabrication live and walk out of the cleanroom and hand the students their what we designed, right? And then there's some fun hands-on activity that we do that relates to current research at Cornell University, and then give them an opportunity for further exploration, something to take home, a little bit of reading material, and generally some of the demo kits just go home with them as well. Atypical CNF youth visits. This year we had 3 micron chip camps, 120 junior high students each came to our facility for a whole extravaganza of all things nano. The picture on the top left is them spilling into a lecture hall at Cornell campus, and my blood pressure right up through the roof. But we had a great time. These were really successful events. It was quite a bit to organize, but it was a great success, and we had a lot of fun. So everybody's familiar with the next generation science standards. Nanotechnology is sort of the ultimate crosscut. I'm going to show examples today that cover biology, nanorobotics kind of falls into physics, material science and earth science are closely related, and chemistry as well. So we can tie all these things together very nicely. And one of my peer educators that I work with sort of had a brilliant insight not long ago where he said, we teach all these students these esoteric concepts like the size of the universe and light years and the diameter of the sun and all that stuff that can be quite difficult to comprehend. He said, why not do the same thing, but smaller? And he says that nano is actually a lot easier for students to comprehend because you work from the size of a human on the meter scale and you work your way down. It's much simpler and it feels closer. Oh, we've got lots of classroom content. So Nano's magazine is free. You can have this in your classroom. You can either go to the CNF website or to nanos.org and register, and we will ship. I think there's 20-something issues available at this point. And we can send them to your school library or directly to your classroom for you to use. And we also have lots of different demos that I've put together. I think we're close to 10 at this point, and I've got more sort of in continuous development. And we target about $1 per student. Most of the time, less than that, generally about half. So here's where we start. What's the smallest thing you've ever made, right? Most kids can respond pretty easily to Legos, right? And so the little dot on the top of a Lego is on the millimeter scale. That's 100,000 nanometers. And then we'll ask, well, has anybody ever made anything at the micro scale? And generally you get a quiet moment until you tell them, yes, you have. Everybody here, I hope you're making blood cells. Otherwise, we're going to have to call an ambulance. And so now we transition, we talk about the size scale of a blood cell is 10 micrometers or 10,000 nanometers. Take that question a step further. Has anybody ever made something at the nanoscale? And the question inevitably is yes. Human DNA is something 3 to 6 nanometers across, right? So now we related that to us, where we are making nanostructures all the time. Now we'll talk about the size scale and sort of relating to the meter. So standard guitar is about 1 meter in length. Again, millimeter scale, we're talking about the pegs on the top of Legos, peas, the wire on a paper clip. Micro scale, now we're talking about the blood cells that we just introduced. There's a nice little picture here of an ant holding a microchip, and one of the nanorobots that was developed in our facility. Moving forward further to the nanometer scale, we've got the strand of DNA, the world's smallest guitar that was made at CNF. And the robot is interesting because laterally, it's on the scale of, say, a cluster of blood cells, right? But the legs that allow it to swim in water are 7 nanometers thick. And here's an important thing. You say, we're going to talk more about that later. The kids really love the nanorobot stuff. I love the nanorobot stuff. It's really beautiful work. But that keeps them engaged if you say, we'll talk more about that later. So a clean room. What is a clean room? We want to talk to our students about that. Well, it's a makerspace, and how convenient that we just had this talk about 3D printing. A makerspace is a place where people can come together and build things, right? And the tools you're going to use are typically 3D printers, a mill, a lathe, power tools. You're going to have some sort of protective equipment on, or safety glasses, gloves, etc. And your measurement techniques are a ruler, tape measure, stuff we're all very familiar with. A clean room is a special type of makerspace. We have very tight control over the cleanliness, the temperature, and the humidity because we're creating devices that are smaller than a grain of pollen. And so on the top right here, there's actually a scanning electron microscope image where somebody was unlucky enough to have a grain of pollen land on their device. It's probably one of the only ones in the clean room. But, a grain of pollen is pretty huge compared to the devices being made. And so if a hair or something falls off of us and lands on our devices, it's ruined, right? The tools that we're using are much different. We're using plasma etchers, plasma deposition tools, and a lot of metrology equipment, things that we can use to measure. Protective equipment is going to be safety glasses, gloves, a face shield, and an apron. That's your personal protective equipment. We also have work protective equipment. The clean room suit itself is going to protect your work from you. A face mask. I once was working with my boss in the clean room, and he's standing there holding a wafer and talking to me, and he accidentally spit on the surface of the wafer and ruined one of the devices. So we wear a face mask. We wear gloves because the salts and oils in your hand are a contaminant. And we wear this clean room suit that stops us from shedding cat hair and stuff all over the lab. The measurement techniques are different as well. We do use a standard microscope, but at some point you're going to be creating devices that can be smaller than the wavelength of light. And so then we move to an SEM, or a scanning electron microscope, where we can see the really small things. Interferometers are used for measuring transparent films. Profilometers are used for measuring topography on a sample. So it's a makerspace, but it's really this very tightly controlled scientific experiment, the entire lab. So the entire lab, you're going to want to see this. There's a QR code here. You can visit the CNF clean room from anywhere. All the little red dots that you see are all the tools that are in the lab. They can be clicked on to learn more about them. The green tags are educational videos that we've put in. You click on a green tag, it goes right to YouTube. And it works on smartphones, tablets, computers, Chromebooks. It loses a little bit of functionality on a VR headset. And so just to give you a quick preview, I'm going to jump to this screen. Everybody can see that? And so
yes, it's coming through, Tom.
All right, so this is right on our website. There's instructions on how to view the virtual experience. You come down, you'll click on this picture, and it's going to take you right into the clean room. It starts out right in the gowning room. There's a short little video right here on how to get suited up in a clean room suit by yours truly. There's an intro about CNF, and clicking the little circles on the floor, you can travel all around the facility, learning about the various pieces of equipment. This is a really neat activity that you can engage your students with and maybe create a little quiz based on what they're learning in these videos. You can jump back to this dollhouse view and sort of drag and drop and move all around the clean room and explore the space. And like I said, every one of these little green dots is a different educational video about some of the content in the facility. So really neat, useful tool, free. It's on our website. Get a hold of me if you'd like to develop some content around it. So back to the presentation. That was my first switch. So how do we use all these specialized tools? Well, it really boils down to three main processes. Lithography, where we're going to coat our wafer with some sort of resist material, pattern it using either light or an electron beam. And from there, there's two basic techniques. We're going to deposit material in those open areas and then remove the resist material. So now you've maybe made some electrodes. Or we can etch material away that's under that. And then it's sort of rinse and repeat, right? So the processor that's powering your smartphone has roughly 80 layers in it that make it, the functional part of that device is about 80 to 100 layers thick, and it's the thickness of a sheet of paper. So really incredible stuff that we can do in the lab with those three basic processes. The fourth one is measurement, right? For every step that we do, we're measuring and inspecting these things constantly to get the best outcome. What do all these tools make? Well, the industry is pretty massive. Computers, cell phone technology, solar cell technology. Your car, as we all found out back during the chip shortage, is loaded with sensor technology and chips, right? Specialty coatings, display technology, AR and VR. I always love asking the audience. When I first started asking how many kids have a VR headset, you'd have a handful or two. Now they're getting very common, and the audience is thrilled to say, hey, I have one of those. Battery technology and even biomedical devices are developed in facilities like in a clean room space. So all the things that make our lives great. There's a really fun video here that was developed by NiceNet. In the interest of time, I'm going to jump past it. I hope nobody minds. It's like 3 minutes long, but it is a fantastic introduction for your students. It gets them laughing, excited about the content. And if you just search NiceNet on YouTube, they still have a lot of really great content on there to sort of introduce the basic concepts to your students. So what does CNF make? Well, it's a little different than what the industry does, right? The industry, we have very similar tools to what industry does. They use theirs to print money in the form of computer chips. We use our tools to do cutting edge research. So stuff that really isn't going to be a consumer technology for maybe 10 years or more. So we do some electronics work in our facility, but that's not the limit. MEMS, not memes, is micro electromechanical systems. And so the accelerometer that's in the bumper of your car, when you hit another car or a deer or something, that's what triggers the airbag, right? That's a MEMS device. And it's very similar to the accelerometer that's in your phone, where when you tilt the screen, it automatically adjusts. There's a little accelerometer in your phone that's doing that measurement and letting the phone know, hey, I want to watch a video in full screen. Microfluidics is a huge part of our research. So lots of people are utilizing the technology that was developed for the electronics industry to study human cells and physiology, and working on a cure for cancer and lots of applications for using the technology in our facility to study biomedical devices. Quantum computing, Sensors of all sorts are constantly being developed downstairs. The one in the picture here is really unique. Everybody's familiar with the concept of, say, going to the hospital and having some sort of sensor implanted. This sensor is a plant implantable that was developed at Cornell, where it can be implanted with a little incision into the side of a grapevine, and they're Bluetooth connected. You can spread them out throughout an orchard. And now it's measuring the water potential in the stalk. So you can tell exactly what areas of the vineyard require water. So we're wasting less water in agriculture. So this was developed at Cornell, and now the company is based in California, where water is a much bigger issue than in upstate New York. Very cool technology nonetheless. And then lots of photonics research as well. So the integration of light and electronics is, a big part of our lives. The display on your phone, the TV in your living room, the display on your VR headset, that's all photonics development, and that's a really big field of research right now. So again, the NNCI network and facilities like CNF are making the cutting edge devices of tomorrow. So at CNF, we have our little Guinness Book of World Records sort of Hall of Fame. We tend to make the smallest something pretty regularly, but these are just some fun ones. The world's smallest self-folding origami bird is actually part of the micro or nano robotics program. It's really incredible. So this is going to start out as a flat sheet, and with a small applied voltage, it folds itself up into the shape of an origami bird, and then can unfold itself as well. It's really neat, and we can make a lot of different shapes with this material and contract. You could almost envision a box that you could fold up with some sort of something in it, maybe a drug that you want to deliver it to a certain part in the body and then have it open up, right? So really cool technology. Again, we'll get it more into the nanorobotics as we move along. The CNF made the world's smallest guitar some time ago. The strings on the guitar are 6 nanometers in diameter. So why would you make a really small guitar? Well, what does a guitar do? When you strum the strings, they resonate. There was a professor that wanted to study resonance, the vibration of nanoscale structures. And so he was going to make these suspended wires and decided, let's build a guitar around it. That'll be cool. You can't strum the strings of a nano guitar with a pick. They actually were exciting it with a laser. So a laser pointer shined on you or I doesn't really have much force. It can't move us, but you can actually shine a laser on the strings and they begin to resonate. The world's smallest bell tower. Back during COVID, one of my coworkers got the plans for McGraw Tower, the bell tower on the Cornell campus. He drew it brick by brick, every stair, every bell, and all the features inside the bell tower. He made the first one 1 millimeter tall. So we have this very high resolution 3D printer in our lab. And then he did a second iteration that was only 300 microns tall. So that's the height of 3 human hairs stacked on their side. A human hair is about 100 microns in diameter. So another really cool technology and a really cool use for it, I guess, as well. So nanorobotics, I promised, right? So here's a fun little video that leads into the nanorobotics program at CNF.
These are the legs of a tiny army of robots. So small, they are dwarfed by a single-celled paramecium. 50 years of development in microelectronics have given us a fantastic array of tiny computer systems. But that is only half the puzzle. A robot also needs to move. And now, researchers have created a brand new type of actuator which can do it, giving the tiny brains some brawn. Up until now, making moving parts at the micron scale has proven tricky. Conventional designs often don't function very well when they're that small. while others work, but rely on mechanisms like magnetism which can't be easily integrated into existing electronic systems. But the new design, called a surface electrochemical actuator, can be fabricated using similar processes to those used to produce microchips. That means the tiny legs can be added directly to the devices that control them. To make the legs, a 7 nanometer thick sheet of platinum is coated on one side with an inactive material like graphene. The legs are then patterned using a technique called lithography, and the excess material is removed. In order to work, the legs need to be in water, but the concept is relatively simple. When a current is passed through the platinum, charged water particles are attracted to the uncoated surface. The force of these particles binding to the metal creates stress on one side of the sheet, and that is what makes it bend. By reinforcing sections of the sheet, the bending can be controlled more specifically, and voila, a tiny robot leg. The robots are equipped with 2 minuscule solar cells. By shining a laser on each one, researchers can create the voltage which activates the front or back legs. These new actuators allow the tiny circuit to move, and because they are created using the same well-understood manufacturing processes as semiconductor electronics, their production can be easily scaled, making millions of tiny robots at the same time. Swarms of robots so small that they can be injected through a hypodermic syringe, and collected using a pipette. Now, at the moment they can't do much, but their compatibility with existing microelectronics makes them versatile. In theory, new actuators based on these designs could be combined with more complex devices to carry out a whole range of more sophisticated tasks. The researchers have pointed to everything from fighting cancer to tackling crop pests. But that is decades away. Time will tell if these first small steps for microrobots could be a giant leap for microrobotics.
Okay, and there's other ones. So the first one was rather simple. They've come a long way though. One of our researchers in the lab proposed a bubble-powered micro-robot where you have the solar cells on top, water goes in, hydrogen and oxygen come out the tailpipe. When she first proposed this, I was like, well, that sounds like it's never going to work, but let's try. So she went down in the lab and got to work, and she actually made it function. And so on the top left, you see one that's still attached to a silicon wafer. It's bubbling away. It looks like everything would work nicely, maybe more bubbles on one side than the other. So maybe it would just spin around. But when I first saw this video, I was pretty blown away. Here's one freely swimming around, and the bubble right there on its tail is the size of a human blood cell. That's about 10 microns in diameter. So really incredible innovation. It took a lot of tests to make that work, but a really neat advancement. And other versions of these robots have come a long way, where Michael Reynolds, one of our other scientists in the lab, developed some of this stuff. We were having a discussion, and I said, have you ever considered making one of these walk how an ant walks? And he says, well, how does an ant walk? Well, they basically have this triped gait where they're alternating from side to side. And he's like, oh, well, that's interesting. So he did it. He made a little nano robot or micro robot that walks like an ant with that triped gait. And so it's powered by light, and it'll just keep continuously walking all over inside a petri dish full of water. But they wanted to add more control to it. And so this next one is basically the world's smallest remote control robot. So right now you'll see it's kind of meandering along, and in a moment he's going to send it a command with a pulse of light, and you're going to see it change speed, just like so. And the neat thing about this one is you can see some of the computation that's actually on top of the robot. So very cool stuff, a really neat project. There's quite a bit more that I could show, but in the interest of time, we will keep moving and get into a demo. So now I'm going to stop sharing for a moment. There's two different nanorobotics demos that we've put together. Here's the one that we're going to do today. I can share these via PDF. There was one that we put together that's a bubble-powered robot. So similar to the BubbleBot, modeled after the classic kids toy. I'm a huge toy nut. So everybody's gotten one of these out of a cereal box at some point. But those are kind of expensive. These are like $6 or $8. So we actually recreated that using baby carrots, toothpicks, and baking powder. And we can make a little submarine that'll go up and down in liquid. But the other one is really neat. It explores the concept of a bimorph and sort of how those legs work, how they're able to bend, right? So this is a simple bimorph demo that you can purchase online. You've got two different metals. So one side is steel, the other side is brass. They have a different thermal coefficient of expansion, right? And so if we take and we heat it up, try and get the angle right here for everybody, you'll see it starts bending, right? Because one material expands more than the other when it's heated, okay? Well, there's another simple demo that we can do in the classroom using the fortune teller miracle fish. So another Cracker Jack box toy that's supposed to be predicting your fortune. And it works exactly the same way as the legs on one of these robots, right? So we put it on our hand, it starts curling up, okay? So, geez, that's like magic. So we just showed this bimorph demo, right? Where we use a lighter or a heat source. We'll ask the students, so how does this fish work, right? And they're gonna say heat, and you're gonna say, great guess, but it's not heat. And so the next step is to take a couple of drops of water on a paper towel as an experiment. And I'm not going to drop this camera today. And we'll set it there. Ah, look, it magically curls up just on a drop of water. So really simple concept, nice way to convey, the content on how the arms on these robots are actually working, and simple, inexpensive, and easy to implement. So now jumping back into Zoom, I'm going to reshare and go here. Oh, wait, no, this one. Sorry. And I need to make sure I still have my audio shared. We've got more videos coming. So two really simple demos that we can share out with everybody. I cannot mail you baby carrots. That's probably not going to work. But we can get you the rest of the supplies if you need. So other cool projects at CNF are biology related. So we're looking, research groups are coming in the lab and studying cancer metastasis. And so now cancer cells are uniquely able to pass through very narrow pathways in the body and get to places where even drugs can't be delivered. They can get past the blood-brain barrier, which is a real problem. And so they're making these little nanostructures in the lab to push the cells through, and sort of, we have like a cancer cell torture program at the CNF. And hopefully eventually this leads to some sort of breakthrough. There's a lot of potential for this research. My degree was actually in bio-based microfluidic devices as well, where I came to CNF to fabricate my devices back when I was in college at the University of Buffalo. And we're even making devices to study antibiotic resistance on chip, right? So microfluidics are sort of a big part of our society. I'm going to show you a demo in just a moment where the students are actually going to create their own version of a lab on a chip, similar to a COVID test, actually. And so I've got two more demos to jump into. So we'll stop sharing again. And we'll come over here. So another neat concept in biology is, hold on, diffusion, right? So a lot of the oxygen being delivered to your capillaries is diffusion based. And so we've got an edible experiment this time. We talk about some of the basics of microfluidics, laminar flow versus turbulent flow, things of this nature. And then we'll take an array of either Skittles or M&Ms. If you have a student with a peanut allergy or something like that, you can use Skittles. They work very nicely. Just arrange them on a paper plate and add a little water. And because there's no flow here, we should get some very nice diffusion-based mixing moving toward the center and forming this really nice rainbow where everything lines up super nice. And the students can even get creative and maybe put some things in the center that are going to bleed outward in their color. The other part that you can add to the experiment is hot water versus cold water. So I just added hot water to it to make it happen very quickly. Cold water will take a little bit more time. Cool. All right, the next microfluidic experiment where the students are going to make their own little COVID test is actually pretty simple. We're going to take some chromatography paper. You coat the back side of it with some packing tape. You're going to drop it on the floor. You're going to color your microfluidic channel using crayons and hold it under a hairdryer on high heat for a minute. What's going to happen is that wax is going to bleed down into the the chromatography paper and form a wax seal all around here. So the fluid is going to stay in the channel. And I have one right here. And so I've got two random powders here on this on the paper. One is baking soda, one is baking powder, and I've got water. And I'll start adding droplets at one end, and we'll see that everything stays in the channel. And when it gets to the other end, only one of them should react. My paper is sort of bent upwards, so I'm not getting much flow here, but we can add droplets. You can repeat this experiment. We normally have the students do 2 of them, where one of them uses water, the other one uses vinegar. Oh, found a leaky spot. And you should get a nice fizzing reaction with water only in the baking powder, not in the baking soda, right? But the fluid should primarily stay right in the channel. And I'm not sure you can see the fizzing, but this is our baking powder. We're producing carbon dioxide. I've overflowed in a couple spots where I left a gap in there accidentally. The vinegar reaction, you actually get both samples bubbling, but you get both samples bubbling, but the baking soda will bubble significantly more than the baking powder. Cool. All right, so here's another fun game that I like to play with students. It's called, is it magic or is it science? All right, so I have a spoon, but I've been talking a lot, so I'm going to make a drink real quick, some hot tea. So is it magic or is it science? So I have this spoon that looks like a normal, ordinary spoon. You can trick your students, say, oh, I'm just making a drink for myself, and we'll mix up our tea, and something really cool happens, right? So the spoon is made of gallium. So you can get a gallium spoon mold on Amazon. It's pretty inexpensive. And it's a lot of fun. It's kind of shocks them when they first see it. But this is gallium. It melts at 30 degrees C, and the human body is 35. And so this is pretty safe to play with in the classroom. And afterwards, it's pretty easy to clean up. It's going to solidify in this beaker. And as the water cools down, and then you can recast it in your spoon mold as you see fit. The next one is this really interesting piece of wire, right? So not many students have had the chance to play with this material, but it's shaped memory wire. So this stuff has come down quite a bit in cost over time. And so the piece I've got here is 6 or 8 inches long, and it costs about 50 cents, right? And so this is a blend of nickel and titanium. Kind of give it to the students, have them play with it. It's boring wire until you take a nice piece of, or a nice dish of hot water, and it instantly goes back to its original straight form, right? And so now we can talk about material science and some of the interesting things that we can do in that field. So this is a blend of nickel and titanium, where it's doing a phase change reaction, where you're cooling it down and then deforming the crystal lattice. And then when you heat it, it snaps back to its original shape. This is one that gets my favorite quote every time. My favorite quote in any outreach event is, "That's so cool. It lets me know that I've done my job for the day." And this one gets them every time. It's a really fun material to play with, and then get them thinking about what you could use it for. Like, what could you use a material that always snaps back for? There's a worksheet that goes with it based on nanomaterials research and talks about its application in heart stents. It's an incredible device that saves people's lives daily. You know, it's to the point where it's now an outpatient procedure where it can unblock a blocked artery using this material. When it sees the body's temperature, it expands and can move a clot out of the way. Great stuff. And there's more we can do with materials science. So all materials have interesting properties if you look close enough. So everybody's familiar with aluminum foil for wrapping up tools or food, aluminum bars for making parts. But if you make aluminum with just a pinch of nitrogen in one of our tools, you actually get a crystal resonator. And so this SEM images here from CNF, the whole thing is coated with aluminum nitride, but the crystal grains are different size depending on what they grow on top of. But aluminum nitride, why is that important? It's in everybody's phone. This is the 5G, 3G filter in your phone that makes our communications work better. There's also a whole lot of nano coatings. So we're running up on time, so I'll skip the video, but a really neat concept is the paint on a 747 jet weighs about 1,200 pounds and is thinner than a human hair. So that's interesting. If we could find a way to reduce that weight, we could save a lot, right? We'd be helping the environment. We make all sorts of hydrophobic coatings and unique coatings in this industry. You'll be able to see this video about the world's darkest material. It's made of carbon nanotubes. And then we'll talk about nanoparticles. So we've talked about carbon nanotubes now. We've talked about graphene, which is a sheet of carbon. And now we can talk about nanoparticles. So these buckyballs are something that a lot of kids are already familiar with. Nanoparticle paint. Could we reduce the weight on a passenger jet significantly by using nanoparticles? Less weight equals less pollution, right? So today it's 1,200 pounds is what the paint on a 747 jet weighs. University of Florida has developed a nanoparticle paint based on butterfly wings. And by arranging structures that reflect light on a surface, we can create these very bright colors. And the really neat thing is painting a 747 jet in butterfly nanoparticle paint would weigh just 3 pounds. So you think about the cumulative number of flights per year, that could have a really significant environmental impact. There's other natural microparticles. Lycopodium is one that you can get at most science outlets. It's hydrophobic and repels water. In bulk, it's not flammable, and you can do some really neat stuff with it. So I have some. So the first thing, I just got it in like a little mustard bottle. It's hydrophobic. So you can put it on top of some water. You put your finger in, and your finger comes out dry, although coated in a little bit of dust. Let's see if I can tilt this camera down. Then we're going to keep disconnecting on top. So by itself, you know, it doesn't really do much. If you put it on a plate, you can hold a lighter to it, and nothing really happens. until you get it to light up. It's pretty great stuff. So this is actually widely used in the special effects industry because you can create a really cool flame. You need some sort of magical command to go with it. How about NanoEducators? And I don't know if I get just enough there. I can blow the flame out. I'm not having luck today. Hold on, here we go. I'll give it a pinch. I can hear it. Maybe we didn't say the command loud enough. Can I get a group NanoEducators all at once? And I'll change my camera angle here.
On the count of three.
Okay. 3, 2, 1.
NanoEducators. Oh.
Wow, nice.
So that's a lot of fun. The students, it's very impactful, right? When you're making fireballs in the classroom, everybody's paying attention. So we can do a lot with that. And it's actually a pretty safe thing that you can do in the classroom that the students will really enjoy. I'll race through the rest of this deck and show you the rest of what I've got. We're almost to the finish line, and then we can take questions. So in bulk, it's not flammable, but it's also known as dragon's breath. Tell the kids not to try this at home. I mean it. And dispersed in the air, it's actually quite flammable. And you can relate this actually to some agricultural incidents that have happened where people are operating a grain dryer and we get all this dust flying around and that can actually ignite. Is nanoscience cool or what?
Awesome.
So cool.
Awesome. So what does it take to become a nanoscientist? These are important concepts to also show your students. So a strong background in the STEM fields is important. Maybe not all of them, but you can focus in on one particular area. Creativity. We don't come up with bubble-powered robots without being very creative. The drive to discover new and exciting things, and the ability to keep trying. None of these things work the first time unless you're incredibly charmed and lucky. Where do nanoscientists work? Well, the short answer is just about everywhere, even in food science. So out there somewhere, there's a person with a scanning electron microscope studying the next generation of Dorito dust, right? You'll find yourself in nanotechnology in just about any field. Here's an important one. How much education does a nanoscientist have? There's some nice links down here at the bottom, but walking through the various educational paths and how long you would plan on going to college for, and then the expected salaries are what people are really interested in. And the nanotechnology, the clean room environment kind of takes all, right? So we have people that work in our facility that don't have any formal college training, right? So there's a place in this career path for everybody. How can I help you? I'm going to stop sharing and maybe we can take a couple minutes to chat.
Thank you so much, Tom. This was great. And I knew that you were going to be enthusiastic about all of this. So thank you so much. If you're willing to stay on and people are also willing to, we can certainly take some questions now, but I also want to remind everyone that this was recorded and Tom is going to share the slides. It'll be a part of that document that is shared after every forum, and his email address is also in the chat and can answer questions that way as well. But we'll stay on for just 5 or so more minutes in case there's questions people want to ask you right now. But we are at the hour, so I wanted to make sure everybody knew there's lots of ways to get this information. All right, I'm just going to open it up for questions now.
And I'm also, if you could just jump in for a second, I'm also putting a survey link in the chat. And Tom, for teachers that are interested in the interested in the kits, how will they get those from you?
I can, if you email me directly, I'm happy to help you. I can set up a slide deck that goes along with the demo sheets. We can work together to sort of curate something for your classroom. Everybody here is probably got a different background or a different focus, right?
Right.
I can share the PDFs of the worksheets. You can get the supplies yourself. Or, if you need resources for your classroom, we can help you out with the supplies if needed.
So are all the PDFs online on your website or no?
They are not, but I can share them with the group.
We would be very interested in seeing those because some of them I knew about, but a lot of them I didn't.
Yeah.
And I've been
There's a
teaching
whole
Nano
bunch
for a
more
while.
that
That's great.
There's a whole bunch more that I'm developing. Edible photonics one is coming up soon, hopefully.
Oh my goodness.
Yeah. Yeah, it's fun, right? That's what this is all about. Showing kids that it's fun, having a blast while you're doing it, and inspiring the next generation of scientists. So
100%. Fantastic. Thank you so much. So does anyone have any questions for Tom?
I've blown your minds. That's what I came for.
Of course you did, Tom. They're just trying to process everything that you just showed everyone. So I'm sure you're going to get lots of follow-up emails because they're all wonderful.
Yeah, please email me. I'm here to help. That's what we're all.
So your email address is in the chat, but I will also put, I have the resources document, the running resources doc that we have for the NanoEducators forum, which I'm going to put in the chat right now. And that has all of the links that showed up in the chat all the way through, and will have your PDF slides linked to it.
Sure.
That's great. So here's the resources doc.
The Zoom recording link would also be included there, and we'll share that with everyone that registered, that you'll get a recap email with all that information too.
Everybody will get to see my camera failure.
We can always cut that out, but I think it's part of the charm.
It goes with it. It goes, right?
So I did know that it's a surface area that makes that material flammable. Is that what because I did also know that wheat when in dispersed in the air is also like very flammable. What was the material that you had in the container?
It's lycopodium, so it's a dried plant spore.
And you can purchase that from a school supply, science
supply. Yep. I have enough of it that I probably will never use the rest in my whole career. But so happy to send a little baggie, for people that need it.
Now that you say that, how much lycopodium do you actually use?
So if you can see, that's how much I've actually got in here. There's not very much in the bottle. You kind of just give it a little squirt on top of the water, right, to make your hydrophobic demonstration. In terms of putting it in the tube, the flame is dependent on how much you put in there. So you can make a really small one. What I was going for, you can have a really cool Harry Potter effect. If you get a little finger full of it and you throw it on a candle and yell nano-osmo, you can get a little fun thing going. But you basically just have a grill lighter and a piece of tubing. You do not want to inhale. You don't want hydrophobic things in your mouth. Bad experience. So I'll just take and do a small one. You give it a little puff. You'll light. Oh, sometimes if you miss the flame, it doesn't work at all. So that's just a tiny little bit. I'm missing it. I think my contraption's out of whack here. Should just go for a big one. It works pretty readily. Yeah, until the end. Now it doesn't want to work at all, and I'm making a big dusty mess in my lab.
I put the link to your video from Millard. What was it? Millard School?
Oh, Millard
Fillmore Elementary School, where you essentially set the auditorium on fire, but it's very impressive to see.
I didn't do that.
What? Who's talking?
I didn't set them on fire. No, it really doesn't take much. You do want to practice it before you do it with your students. but normally it works great. You can actually, if you've got an older level of students, say junior high or higher, you can actually have them do it. Just make sure they point it away from themselves and not at another human. But yeah, it's a pretty fun experiment to do. It's impactful, right?
Umit has his hand raised.
Yep.
Oh, hi. Hi, Tom.
Hi.
Well, thanks for the inspiring presentation. It's always fun to see what the possibilities are with nanotechnology. My question was more about the CNF facility.
Mm-hmm.
Like people who are not in that region, I know you guys are in upstate New York area. Like if I had the opportunity to commute, let's say I have some project, I want to nanofabricate, some device, and I have my plan, I have my execution plan, everything worked out. I'm going to take a trip to your facility, and I maybe know some of the equipment, but maybe I know lithography, but not etching or some of the characterization tools. I don't know. Is there a way to, first of all, to schedule the trip like that, and say like, hey, your plan sounds like maybe I can share the schematics with you or layout, and then somebody from your team would say like, hey, something like this fabricating will take like 5 to 7 days. If you can spend a week in our facility with us, we would be able to help you out. And during that time, perhaps you can stay in a hotel or something. Is something like this possible? Like for someone who's not local, but willing to travel with a plan, is my question.
I just had a conversation with somebody from Clemson, exactly like that this afternoon. We have a weekly technical session every Wednesday where you can come discuss your project with the technical staff at CNF. Then there's some paperwork to fill out and create a project. From there, you would come here. We start off with a safety training and introduce you to the facility. Then you get trained on the individual pieces of equipment. We get you up to speed and running very quickly. And based on the complexity of your project, something simple, you could leave with devices in a week. Something more complex, you're going to want to plan a 2-week stay or maybe a second visit or something.
Awesome.
Like that.
Got it. Thank you. And maybe a quick follow-up question to that. If I'm trained on clean room in a different facility, do I still need to take it for yours as well?
Mandatory.
Okay.
Yep. So every facility is a little bit different, and the rules here are our rules, and so
got you.
Got to get brought up.
And how long does that take? Like typically for someone just starting up, like how long is typical learning curve for basic training to get access to equipment?
Safety training is 1 day plus like 2 hours on the second day, and then if you're a visitor to our facility from afar, we would try and expedite your training with all the tool managers to get you up on your feet.
Awesome. Well, thank you. This was fantastic. I appreciate it.
No problem. Send me an email. I'll get you through the process.
Will do. Thank you.
Tom, thank you so much. One more question, then I want to be mindful of everyone's time. Does Cornell do any type of RET or anything like that to get teachers trained in the clean room in the summertime? I can't remember if you have any kind of summer training program for teachers.
We have done that in the past, and it's something I should talk with Lynn Rathbun about.
Good. I'm glad I'm ending this with a little extra work for Lynn. Well done. So with that, I want to wrap it up because we're already a little bit over, and I know that you are very passionate and could probably stay on here for even longer, but everybody should head home and get their dinner or head home from wherever they are if they're on the West Coast. So I want to thank you again for doing this. We're going to share everything. It was fantastic as always. Marielle and Daniela, if you have anything last comments you want to make, please fill out the survey. Be on the lookout for all of this. And Tom, again, thank you. This was really, really cool.
Thanks for having me.